Okay, welcome back, and today we're going to continue on and finish up the chapter on hypothesis testing, and this is chapter 9, so single populations for the mean and the population or proportion. So we're going to begin the last topic, and it's going to be hypothesis testing involving population proportions, okay? So it's a test for a single population proportion. Okay, so now, a couple of things to keep in mind. Here we go. So just like with hypothesis testing involving for a single population for a single mean, we're going to start with the hypothesis testing, right? So we're going to start with the hypotheses here. So again, our different hypotheses will look like one of these. And so those are the three sets of hypotheses that we're going to consider, okay? Also, we have to know the distribution of, the sampling distribution of p hat, right? Just like in chapter 8 for confidence intervals. So to do the test, we need to know what the distribution of p hat is, and of course, we want it to be normal, okay? So recall that if 1, n is bigger than or equal to 30, 2, the expected number of successes, n times p, is bigger than or equal to 15, and n times q is bigger than or equal to 15, then we know that the distribution of p hat is going to be approximately normal with a mean of p and a standard deviation of p q divided by n. Okay, so that's what we know. So again, just as a review, this is what we call mu of p hat, and this is sigma of p hat. So now, if this is true, and we have this distribution, then we can do our tests, right? So we can do the traditional method, right? So with the traditional method, we can calculate our z star, which in this case would be equal to p hat minus p0 divided by the standard deviation of p0, q0 over n. And of course, why are we using p0? Because that's what we're assuming under the null to be true, whatever the given value is for p0. So we're going to substitute in what we're going to assume, okay? And then we're going to calculate our test statistic based on this formula. And then of course, how do we get our z alpha? Or z alpha divided by 2 if it's a two-tailed test, the same way, right? The same way we did before with the mean is just going to be using inverse norm, okay? But just make sure that we have the correct area to the left, right? And that comes from our alpha, and comes from the alternative hypothesis, right? The alternative hypothesis tells us what test to run. So that's going to tell us what to put in for p, the area to the left, followed by 0 and 1. And that's it. So then what we do, again, we're going to compare our critical value with the test statistic, right? So if our test statistic falls inside the rejection region bounded by our critical value, then we reject the null. So again, same method as before, when we're dealing with the mean, okay? Now, the p-value method, with the p-value method for p, we're going to calculate the p-value, right? So again, p-value depends, how we calculate the p-value depends on the test, right? Whether it's a right tail, left tail, or a two-tail test. So if we, let's say if we just use a left tail test for a second. So if it's left tail, then of course our p-value is going to be equal to the probability that our statistic, right, is greater than or equal to some value. Well, if we're dealing with proportions, okay, we know it's going to have this distribution, right? Well, we want excuse me. We want to know if it's a left tail test, it's going to be less than, right? So we want to know the probability that our test statistic or our sample statistic, you could use either one, that our sample statistic, p hat, is less than or equal to whatever value that we calculated, right? Whatever we calculated from the sample, okay? The sample statistic, right? And so we can use that, and then we can just go ahead and find whatever that value is, right? The probability. And how would we find the probability? Well, we could use normal CDF. Why? Because we know that it's normal. So we could use normal CDF, right? And in that case, we would just put in the lower bound, right? In this case, what's the lowest that we could get for any p hat? Well, we're talking about proportions, right? Or percentages. What's the lowest percentage you can have? 0. What's the lowest p hat you can have? 0. Now, what's the upper bound? Well, it'll be whatever this value is, right? It'll be whatever our p hat is that we calculated, okay? So that'll go here, okay? Whatever our p hat is, I'll just put p hat. Followed by the mean. Well, what's the mean? Well, the mean is under the null, p0. So we're going to put p0 in here. And then our standard deviation is going to be this. So we're going to stick this also in here. So this would be the square root of p0, q0 divided by n. Okay? So as long as we put the correct values into the normal CDF, right? It's normal. This is the mean, this is standard deviation. So as long as we put the correct mean and the correct standard deviation in our upper and lower bound, we'll get the same answer, okay? Now, incidentally, you could, instead of using p hat, you could use the z star, right? And then just use whatever the z star value you got here. And then, of course, it'd be 0, you know, the lowest here would be negative 10 to the 99, and then your upper bound would be your, whatever your z star is. So this would be 10 to the, or negative 10 to the 99. Let me do this. So your lower bound would be negative 10 to the 99. Upper bound is whatever your test statistic is, followed by the mean, which is it's a z-score now, so it's just going to be 0, 1, because you're talking about z-scores. Okay. Either way, you should get the exact same key value. Prove it to yourself and do one of the problems that way. Okay, and then once you have your p-value, depending on the test, just compare it to alpha. Okay? So it's the same thing. So let's do an example. A consumer group asserts that the proportion of households that have 3 cell phones is 30%. A cell phone company has reason to believe that the proportion is more than 30%. Before they start a big advertising campaign, they conduct a hypothesis test. Their marketing people survey 150 households with the result that 60 of the households have 3 cell phones. This data is then used to test the claim that more than 30% of households have 3 cell phones. At the 5% significance level, is there sufficient evidence to support the company's claim? Okay, so what's the claim here? So the claim is that they believe that the proportion of households that have 3 cell phones is greater than 30%. So they believe the proportion of people who have 3 cell phones, so the proportion of households that have more than 3 cell phones is more than 30%. So what does this mean? It's not talking about a mean. It doesn't say average or mean. It says proportion, right? So we're talking about P. So we're saying that the proportion of households that have 3 cell phones is P. And we're saying that that proportion is more than what? More than 30%. That's P0. So now based on this, we can set up our null and our alternative hypotheses. So this is the alternative hypothesis because it does not contain the equal sign. So it's going to be P is greater than P0. But what is P0? P0 is 0.3. Always write your proportions as a decimal in the hypothesis test. So versus, what's the other one? It's going to be P is less than or equal to 0.3. And the claim is the alternative. So now, what do we do? Well, again, this is a right tail test. And step 2 is we assume the null is true. So we assume that what? P is equal to 0.3. And then step 3 is where we're going to write down the information in the problem and then conduct our, test our conditions, see if our conditions are satisfied for the distribution that we need. And in this case, because we're dealing with confidence intervals, we need the distribution of p hat, the sampling distribution of p hat to be normal. That's the key. So now, so the first thing is alpha. Alpha in this case is what? A 5% significance level, so alpha is 0.05. What do they market? They found a sample size of 150. So that's N. And of the 150 households, how many households had 3 cell phones? 60. So now, they want to know, is there sufficient evidence to support the company's claim that the proportion of households that have 3 cell phones is greater than 30%? Well, let's find out. First of all, let's check our 3 conditions. Is N bigger than or equal to 30? Yes. Is N times P? Now here's where we're assuming here, right? So we want the expected number of failures. N times P0 is what? That's going to be 150 times what? 0.3. Okay? So what's the expected number of successes? Well, if you multiply these 2 together, what are we going to get? We're going to get 45. Well, is 45 bigger than or equal to 15? Yes. N times Q0. Well, that's the same as N minus 45. Because if there's 45 successes, then there has to be n minus that, so x is the number of successes, right? So if that's the expected number of successes, then the expected number of failures should be n minus this. So that's going to be what? 105. And is that bigger than or equal to 15? Yes. Now, one thing to keep in mind that I want to make a note to, technically, based on the textbook and the things that I've done, the expected number of failures and the expected number of successes that I've seen has been 10. Okay, and I'm going to double check that, but I know in the PowerPoint and the textbook that I've been teaching from, they say 15, which, but in the textbook, and I've seen this other places, I'm going to double check this, but it says 10. So the expected number, these values are 10. Now they use 15. I'm not sure why, but it doesn't matter. I mean, it'll work. So the expected number of failures and expected number of successes is big enough, okay? So this is greater than or equal to 30, this is bigger than or equal to 15, this is also bigger than or equal to 13. So what does this mean? It means that we now can say that p hat is approximately normal with p equal to what? 0.3. And the standard deviation is equal to 0.3 times 0.7 divided by 150. And so this, again, is what we're going to use in step 4. Okay, so again, this is what we need. Okay, now that we have that, now that we know, now we can go to step 4. And I'm going to do the traditional method, I'm going to do the p-value method, and then I'll show you on the calculator using a function 1prop z test. Okay, so the traditional method, we're going to calculate our test statistic z star. So z star in this case is equal to p hat minus p0 divided by the square root of p0 q0 divided by n. And so what do we get when we do that? Let's find out. So what's p hat? Well, we have to figure that out. What's p hat? P hat is equal to 60 over 150. So p hat is equal to 0.4. So we're going to take p hat minus p0, which is 0.3, and then we're going to divide by the square root of 0.3 times 0.7 divided by 150. And we get 2.673. Or it should be 2.67. 2.67. So now all we need is our critical value. And since it's a right-tailed test, we're looking for z alpha. And so we're going to use inverse norm. Why? Because it's a normal distribution. So now, what do we need to put for our critical value? It's going to be the area to the left, right? Correct? So what we need is the area to the left. But this is a right-tailed test. So what is the area in the right tail for a right-tailed test? It's alpha. So if alpha is the area to the right, then the area to the left must be 0.95. So we're going to put 0.95 in here, followed by what? It's a z-score that we want. So it's going to be standard normal. 0 is the mean. 1 is the standard deviation. And now, what is the critical value for this situation? It's going to be 1.645. okay? One of the common ones. Now, step 5 is our comparison. So now what we're going to do is we're going to compare our z-star, our test statistic, to our critical value. And since it's a right-tailed test, we're going to reject if our test statistic, z-star, falls within the rejection region in the right tail, which means bigger than or equal to. So the question is z-star bigger than or equal to our z-alpha? Well, z-star equals 2.67, z-alpha is 1.645, and yes, z-star is bigger than or equal to z-alpha. And so 6, therefore, we reject the null hypothesis. And then 7, our conclusion. What does it say about the claim? Well, since the claim is the alternative, the phrasing is going to be either either there is strong evidence to support the claim or there is not enough evidence to support the claim, something like that, right? So in this case, we reject the null, and so that means there is significant evidence or sufficient evidence or strong evidence to support the claim. So what I would say is at an alpha level of 0.05, there is significant evidence to support the claim that the proportion of households that have 3 cell phones is larger or more than 30% based on the sample data. And that's the way I would say it. So that is the traditional method. So now let's look at the p-value method. So I'm just going to erase this. So now what I'm going to do is I'm going to use this distribution. So I want to find the p-value. So the p-value, so p-value method. Okay. So in this case, p-value, because it's a right-tailed test, it's the probability that my statistic, my sample statistic, what is p hat, right? That my sample statistic, p hat, is as extreme or more extreme than what I got. Well, what did I get? Well, I got a p hat of 0.4. So what's the probability that p hat is what? Greater than or equal to 0.4. Okay. Now, how am I going to get this? Well, since it's a normal distribution, I'm going to use normal CDF, right? So normal CDF, right? Now, I just have to know what the lower bound is. What's the lower bound for greater than or equal to? Well, it's whatever this value is, because this is the least it could be. So it's going to be 0.4. Now, what's the upper bound? We're talking about proportions, right? Think percentages. What's the largest percentage that you can have of something, right? So if you think of a whole pie, what's the largest percentage of the pie you can eat? 100%, right? You can't eat 150% of the pie, right? So in this case, we're looking at any proportions or any number between 0 and 1, right? 100%, okay? So the largest that this p hat will be is 1. So for greater than, when you're dealing with proportions, your upper bound will always be 1. If it's a less than, right, a left-tailed test, if it's a left-tailed test, then your lower bound will always be 0, because that's the smallest proportion of something you can have. Okay. So anyway, so back to this. So our lower bound is 0.4, our upper bound is 1, and now what's the mean? Well, the mean of the distribution is right here, 0.3, right? So we're going to put 0.3, and what's the standard deviation of the distribution? Right here. I'm going to put in this. So I'm going to put in the square root of 0.3 times 0.7 divided by 150. And so that's what we're going to end up having. And so what do we get for our p-value? Well, let's check the calculator. Now, so the second thing, so I'm going to go to second bars, go to norm CDF. Okay, so it's going to be 0.4, comma, 1, comma, 0.3, comma, square root 0.3 times 0.7 divided by 150, and enter. And I get 0.0038. 0.0038. Okay, now, I'm going to do that p-value a different way, and I'm going to show you that you get the exact same answer. Because when we did the test statistic, right, z star, what did we calculate for z star? Well, our z star value was 2.67. 2.67. So now I'm going to do the p-value, but instead of p hat here and using this, I'm going to use z star. Watch what happens. I'm just going to erase this for a moment. And I'm going to erase this. And so what I'm going to do is I'm going to use my test statistic. I'm going to show you, you get the exact same answer. So I'm going to, my p-value, I'm going to say, what's the probability of getting the statistic that I got, my test statistic, as extreme or more extreme? So that's going to be greater than or equal to what? I got 2.67. That was my z star, my test statistic. So now I'm going to figure out what that probability is, 2.67. So what is the probability of that? Well, since I know it's normal, it's a z-score, it's normal. So I'm going to say normal CDF. What's the lower bound here? 2.67. What's the upper bound here? Well, that's going to be positive 10 to the 99th power I could use, because remember it goes off to infinity. And then what's the mean? Well, what's the mean of a z-score? 0. And what's the standard deviation of a z-score? For a z-distribution, 1. And so let's put that in our calculator and see what we get. So I'm going to go to norm CDF, and, oops, I'm going to go to norm CDF, and I'm going to put in 2.67, comma 10 to the 99th power, comma 0, comma 1. And look at that, I get the same thing, 0038. So you could use your test statistic, or you could use your sample statistic. Remember, from chapter 3 and chapter 2, they're going to give you the same probability or area to the left or right. Okay? So keep that in mind. So now, so here's our p-value. So once we have our p-value, we compare our p-value to what? Alpha. And so here our p-value is 0.0038. Our alpha is 0.05, right? And is our p-value less than alpha? Yes, and look at that. We get the same result, and we should always get the same result. Okay? Now, the last thing is, let's show you the calculator. So now, in the calculator, we are going to use, now I just showed you the traditional method and the p-value method separately. Now I'm going to show you the function in the calculator that will give you both your test statistic and your p-value in the same output. Okay? So we're going to use one proportion z-test, or one prop z-test. And so with this, you're going to put in what is p0, right? It's going to ask you what is p0. It's going to ask you also what is n. It's going to ask you what is x. It's also going to ask you what is your alternative hypothesis, what's HA, right? And then that's it. And then what it's going to do is it's going to give you your z star and your p-value. And let's see if we get the same thing. So I'm going to go to my one prop z-test. So I'm going to go under stat tests. And I'm going to scroll all the way down until I get to one prop z-test, which is 5. Now P0 is 0.3, X was 60, N was 150, and our alternative hypothesis is greater than. And so now we calculate, and look at that. I get the exact same values. I get the exact same values. So I get 2.67 and 0.0038. That's it, guys. That's that easy. The only difference is we're doing hypothesis testing for P, not mu. So we're doing hypothesis testing for population proportions instead of dealing with population means. Okay, but the same 7 steps. Okay, so now let's see here. I want to, let's see here. Okay, let's try this one. In a study of 4,200, or actually, let me do this one. It says, marketers believe that 92% of adults in the United States own a cell phone. A cell phone manufacturer believes that that percentage is actually lower. A random sample of 200 American adults are surveyed, of which 174 report owning cell phones. Test the manufacturer's claim using a 5% level of significance. State the null and alternative blah, 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 blah. Okay? So let's do that. So now, the marketers believe that 92% of adults in the United States own a cell phone. A cell phone manufacturer believes that percentage is actually lower. So what do they mean by that? It says a cell phone manufacturer believes that percentage is actually lower. So meaning the percentage of adults in the United States who own a cell phone is actually lower than 92%. So let's write that as their claim. So they're claiming that the proportion of adults in the US who own a cell phone is actually less than 92%. And so there's our claim, okay? So that this time I went directly from the sentence to the symbols, okay? So now I know that this is the alternative hypothesis. So this is going to be P is greater than or equal to 0.92 versus P is less than 0.92. And this is the claim. And in this case, it is a left tail test. And so now this is step 1. And step 2 is we're going to assume what? We're going to assume that P is equal to 0.92, right? We're going to assume the null is true. Now 3, let's write down what they tell us. Well, this survey, they randomly surveyed 200 American adults, right? So N is equal to 200. Also, alpha is equal to 0.05. And of the 200 American adults that were surveyed, 174 of them said that they owned a cell phone. So that's X, right? Now, what else? That's it. So now let's do our checks. Is N bigger than or equal to 30? Check. Well, is N times P0 bigger than or equal to 15 or 10? So what's P0? P0 is 0.92. So what is 200 times 0.92? Well, that's going to be 184. Well, 184 is definitely bigger than or equal to 10 or 15. Now let's do N times Q0. Well, this is 184. That means what? How many do we have left over? We have 16. Right? So n times q0 is what? 16. So is 16 bigger than or equal to 10 or 15? Yes, it is. Close, though. So now, again, we got the conditions. So what do we know? We know that p hat is going to be normally or approximately normally distributed with a mean of p. Well, what's p? 0.92. And the standard deviation is going to be square root of 0.92 times 0.08 divided by 200. So now, that's the key thing. So this is what we know, okay? Based on this, this, and this. Okay? So now that we know that, now we can go to step 4. So now step 4, again, I'm going to use the one prop z-test and use whatever method I want. So just don't forget how to do the traditional method or the p-value method, right? You should know how to do both if asked to, okay? So now, one prop z-test. And what are we going to put in? Well, we're going to put in P0, we're going to put in N, we're going to put in X, we're going to put in the alternative hypothesis. Okay? And so let's do that. So let's go to our calculator, go to Stat Tests, and I'm going to scroll down to number 5 for one prop z-test. P0 in this case is 0.92. X is what? X is 174. N is 200. And the alternative hypothesis this time is less than P0. So I'm going to choose the less than. And now our critical value, or not critical value, but our test statistic Z star is now negative 2.61, and our p-value for this test statistic is 0.0046. Okay, so now, all we need to do either one is just our critical value. So let's just, for a minute, what is the critical value? So what is Z alpha in this case? Well, it's a 5% significance level, right? And it's a left-tailed test. So the critical value is going to end up being a negative 1.645. And if you don't know that, just use inverse norm, okay? But you're going to get a negative 1.645 for your critical value. So once you get your critical value and you have your from one prop z test, now you can do either method. So if you want to do the traditional method, then you're just going z star, which is equal to negative 2.61, and z alpha is equal to negative 1.645. And based on the left-tail test, we're going to reject if this z-score, excuse me, yeah, this z-score, this test statistic is less than or equal to our critical value. And in this case, it is, right? It is less than or equal to that. So then 6 is what? We are going to reject the null. And so we are going to reject the null. And the last step, the conclusion. What's the claim? The claim is the alternative. So is there enough evidence to support the claim? Yes, there is. Okay? So we would state again, at an alpha level of 0.05, there is significant evidence to support the claim that the proportion of adults in the US who own a cell phone is less than 92% based on the sample data. Okay? don't forget how to phrase the conclusion. Non-technical terms, mention the significance level, mention the fact that it's based on the sample data, and does it support the claim or does it not support the claim? Does it reject the claim? Does it fail to reject the claim? Those sorts of things. Okay? Okay, let's do the next one. Okay, so the next one says, let me see where we're at. Yeah, let's go. So, and the next one will say, it says, in a study of 420,019 cell phone users, 172 of the subjects developed brain cancer. Test the claim that cell phone users developed brain cancer at a greater rate than that of non-cell phone users. So here's a great example of where statistics can help us determine whether something is causing something else, right? So does regular cell phone use cause or if there's a significant association between using cell phones and brain cancer, okay? So we're going to use the data to see, is people who use the cell phone, is the incidence of brain cancer, right, or the proportion of users who use a cell phone regularly, is the proportion of those users that develop brain cancer significantly higher than what we see in the regular population overall, okay? So it says here, in a study of 420,019 cell phone users, 172 of the subjects developed brain cancer. Test the claim that cell phone users developed brain cancer at a greater rate than that of non-cell phone users. Now, the rate of brain cancer for non-cell phone users is 0.034%. 0.034%. Okay? So now, use the, since this is a critical, so here's another one. Since this is a critical issue, okay, this is very important, right? This is a very important issue. Here's the alpha level, right? Remember what alpha means. Okay, alpha is the probability of making a type 1 error, right? What is the type 1 error? It's rejecting the null when, rejecting the null when you shouldn't have. Okay? So we want that probability to be very small. We don't want to reject the null unless we want to reject the null. Hold on a second. How do I want to say this? So since alpha is the probability of a type 1 error, and a type 1 error is rejecting the null when the null is true. So rejecting the null when we shouldn't have, okay? So we want the probability to be small, okay? And since this is a critical issue, we want to make that very small. So we're going to use alpha of 0.005, okay? So now, let's test the claim. Now, the claim is that cell phone users developed brain cancer at a greater rate than non-cell phone users. Well, what's that rate? 0.034%. So in other words, they're claiming that the proportion of cell phone users, who develop brain cancer is greater than the proportion of non-cell phone users who develop brain cancer. And that percentage we know to our proportion is 0.00034. So an extremely small percentage, right? 0.034%. So as a decimal, 0.00034. So now this is the alternative, so it's going to be p is greater than 0.00034 here. This is going to be p is less than or equal to 0.00034. Okay? And so our claim is this, right? This is the claim we're testing. So now again, we're going to assume that the null is true. So we're going to assume that p is actually equal to 0.00034. And so now what's the information? So here's the alpha level. So alpha level is 0.005. Okay, very small alpha level. So now, what else do we know? We know n. N is what? 420,019. Of this sample size, how many developed brain cancer? 172. So now, let's talk about that type 1 error again, right? So what is type 1 error? So what are we going to assume in this case? We're going to assume that there's no difference, okay? If the null hypothesis is indeed true, right? That's the part of the type 1 error. If the null hypothesis is indeed true, that means the proportion of cell phone users who develop brain cancer is equal to 0.00034. And we reject that. If we reject that, that means we're saying that it's greater than when it really isn't. Okay? That's what we're saying. Let's see here. Okay, let me just. Okay, so anyway, that's what I'm looking for. Sorry. Okay, so now let's continue on. Okay, so anything else here? Okay, so obviously at this point, we can definitely check the conditions, right? It's obvious that this is bigger than 30, so we definitely have that one. If we take n times p0, well, that's going to be what? P0 is assumed to be this, right? So if we take 42019, so again, let's do that on the calculator. So if I take 420,019 times 0.00034, I get a approximately 142.8, so 143. So I get 143, which is definitely bigger than or equal to 10 or 15, okay? And then if you subtract that number from this number, well, that number definitely is bigger than 15 too. So n times q hat is definitely bigger than 15. So we know, based on our data, that the distribution of p hat is going to be approximately normal with a mean of p, which is equal to what? 0.00034. Okay? And then the standard deviation of that would be the square root of 0.00034 times 0.99966 divided by 420,019. And so this, again, is the distribution we need and that we're going to use for step 4. Okay. So now I'm going to use one prop z int or z test, and I'm going to plug in the information. I'm going to get my z star and my p value. Okay, so I'm going to go ahead and plug in my values. Okay, so P0 is 0.00034. My X is 172. My N is 420,019. And this is a right tail test, so I'm going to do greater than. My alternative hypothesis is greater than. And then calculate. And here is my p hat. Or actually, not p hat, p value. It's 0.0073, and my z star is 2.44. And so again, I can either do the traditional method, and since my alpha level is 0.005, right? So I can use inverse norm. So here, z alpha, it's a right tail test. So I'm going to use inverse norm. Now, what's the area to the left? Well, this is the area to the right, right? This is the area to the right. Then the area to the left has to be 0.995. Okay, and if you recognize this, this is a 99% confidence interval also, right? So if we put in 0.995 and then 0, 1, we should get 2.576 as our critical value. Okay? And yes, it is. Okay? So again, what are the common ones? And then, of course, we could do the traditional method, compare our test statistic to here. So in this case, it's a right tail test, right? Which means we're going to reject if our if our test statistic falls within the rejection region on the right side, greater than or equal to. So z star is equal to 2.44. Z alpha in this case is 2.576. And is our test statistic greater than or equal to our critical value? No, it is not. So therefore, what's the conclusion? We fail to reject the null. And so based on the claim, is there enough evidence to support the claim? No. because we failed to reject the null. We're assuming the null is true, and we failed to reject that assumption, so there's not enough evidence to support the alternative or the claim. So at an alpha level of 0.05, there is not enough evidence to support the claim that the proportion of cell phone users who develop brain cancer is greater than the proportion of non-cell phone users who develop brain cancer, based on the sample data. So that's it. And then, of course, the p-value, you can use the p-value too, right? So p-value, what's the p-value? 0.007. So p-value is equal to 0.0073, and our alpha level is 0.005. And is our p-value less than alpha? No. And of course, we get the same result. Okay? And that's it. So that's going to end chapter 9 with hypothesis testing. Next time, we're going to get together and we're going to talk about hypothesis testing involving two populations. So we're going to go through everything, but it's going to involve two means or two proportions. And so we're going to look at the differences between means or the differences between proportions, and we're going to ask ourselves, is there a significant difference between the two populations? Either the two population means or the two population proportions, and we're going to use the same 7 steps. It's just going to, our hypotheses are going to look differently because we're going to deal with two means now, and we're going to be considering the differences between means and the differences between proportions. But then everything else is going to look the same. Our test is going to look different because our calculations are going to be based on two populations instead of one. And I'll see you next time.